In the last class, we were looking at stabilizing third order system, and we all one plus s by omega d, and we saw that well, the whole idea in placing this 1 plus s by omega d, having this extra pole, is to make the frequency response of the loop gain resemble that of a first order system, right? And if we draw the log magnitude of the loop gain versus log omega, we basically have say for this choice of is omega d1, and this goes 20 dB per decade up to here. And then starts to go at 80 dB a decade, right? Now, this is so evidently, I mean, over the useful frequency range of interest, right? And what did we say the useful frequency range of interest was? I mean, at all frequencies where the loop gain is greater than 1 or around about 1, as long as at those frequencies, in that frequency range, as long as the frequency response of the loop gain function resembles that of a first order system, we should expect that the stability properties also pretty much resemble that of a first order system, right? And of course, the at this frequency, at omega naught and thereabouts, the frequency response deviates from that of the first order system, but at that point the magnitude response is so small that the closed loop gain, remember, is nothing but 1 over f times loop gain by 1 plus loop gain. So, if the angle of the loop gain, for instance, becomes 180 degrees, but the magnitude is very, very small, then that 1 plus loop gain can never become 0, and therefore the the system, we don't really worry about the thing becoming unstable because the magnitude response is so small already. Okay, so all right, so so that brings us to the next question. Well, if we what have we paid for? I mean, what is that we are paying? So thanks to dominant pole compensation, therefore we have the luxury of having a large DC loop gain, which is A naught cube f, while at the same time inheriting the stability of a first order system, right? But there is no free lunch. So what have we paid in this whole bargain? We have seen that this the bandwidth of the system has gone down. What is the bandwidth now? A naught cube f times omega d1, right? Whereas earlier the loop gain was had a very high magnitude all the way up to omega naught, right? But I mean that didn't really help because, well, the system was not stable in the first place, right? I mean, it's like basically having 300 crores in my bank account, but my bank account is frozen by the enforcement directorate, and therefore I can't draw any money, right? It doesn't help to have any money like that, right? So so this is so here at least you have you have less bandwidth, but at least the whole system works. Now the next obvious question comes is, hey, what is so special about omega d1? What prevents me, for instance, from choosing, I don't know, say omega d2, where for this choice of omega d2, I have this Bode-plot, correct? And what is the difference? We see that with omega d1 versus omega d2, well, the frequency at which the response deviates from true first order behavior, right? At that frequency, the gain with when you use omega d1 is the gain, the loop gain at which the frequency, the frequency response deviates from true first order behavior is much lower when you choose omega d1 versus omega d2, and consequently, it's fair to say that choosing omega d1 results in a better approximation to a first order system. Having said that, however, right, here also it seems like, well, when the deviation occurs, the magnitude response is much smaller than unity anyway, so it doesn't look like this is going to give us any problem either, correct? So in other words, we need to find some way of quantifying the closeness or lack thereof from the response of a true first order system, right? So one immediate obvious advantage of choosing omega d2 is that the unity gain frequency is now definitely much larger than what we had with omega d1, right? So the question is, how do we quantify the resemblance to a true first order system? And that, as we discussed in the previous class, is by measuring the phase of the loop gain. So for a true first order loop gain function, right, what is the angle of the loop gain at the unity gain frequency? Let omega u be denote the unity gain frequency, right? So if you had a true first order system with, say, omega d1, what would be the angle of the loop gain at the unity gain frequency? It will be approximately minus 90. Why do I say approximate? Because it is tan inverse of some large number, which we say is 90 degrees. So it's the angle of the loop gain is negative pi by 2 radians. All right. Now with our omega d1, as dominant pole. When I say dominant pole, it obviously means that there are other poles, right? What is the angle of the loop gain at omega u? First of all, what is omega u? A naught cube f omega d1. Now I'd like to add a small warning here. See this omega u being a naught cube f omega d1 is only true if, under what circumstance? Is it exactly equal to a naught cube f omega d1? The higher order poles will also cause a magnitude. What is the definition of omega u? The frequency at which the magnitude becomes 1, right? So the assumption here is that the higher order poles, the 3 poles at omega naught in our example, are not causing an appreciable change in the magnitude response as compared to that of a true first order system, right? So that will only be true if the unity gain frequency is sufficiently low compared to omega naught. Is that clear? So that is the assumption that you have to bear in mind when you make this. If the unity gain frequency gets very close to omega naught, right, then you will find that this is not quite true. There is going to be some error in. Anyway, so this is something that you need to. So the angle of the loop gain at omega u is therefore what is it? Well, there will be 4 contributions, one due to omega d, and 3 due to each of the poles, all of them which are sitting at omega naught. So this is basically minus pi over 2 minus 3 tan inverse omega u over omega naught. Okay. And sanity check, as omega naught tends to infinity, we should get minus pi by 2, all right. And so therefore, the if we chose omega d2 as the dominant pole frequency, what comment can you make? Omega u is now, we just have to replace omega d2 instead of omega d1 in all our expressions. So, the angle of the loop gain at omega u is nothing but minus pi over 2 minus 3 tan inverse omega u over omega naught, right. And note that this omega u and this omega u are different, right. So, which of them, which choice of omega 1 or omega 2 will have a larger phase lag? Omega d2, right. And so, therefore, the deviation of the phase from 90 degrees is an indicator of the resemblance of the response to a true first order system. Does it make sense, right? And the phase measurement is a lot easier than, I mean, is a lot more easy to do than magnitude, because when the deviation occurs, the magnitude may be so small that okay. Another way of looking at it from more theoretical angle is that a pole affects the phase a lot earlier than the magnitude, because at low frequency the magnitude is remember that the magnitude is an even function of frequency. So therefore, at low frequency the magnitude remains approximately flat, right, whereas the phase is a linear function of frequency, and therefore you will get something which is right. So so now that brings us to the next point, which is what you do not want is the angle of the loop gain at the unity gain frequency to be 180 degrees. If that is the case, the system will be unstable, and of course it comes out of the math, but let me give you some intuition why that makes sense. So, let us say you have a system, this is the forward amplifier, this is the feedback block. Now, the question is, so let us assume that at some j omega x, let A of j omega x times f be one angle 180 degrees. All right. I mean, from the expressions, of course, it is apparent that what comment can we make about the closed loop gain at omega x at the frequency j omega x? Infinity. So, there are two poles at plus minus j omega x. So, let me give you time domain intuition about as to why this will lead to instability. So, for example, so I am going to break open the loop. So, now there is no feedback loop to make this unstable, correct. So, and then what I am going to do is I am going to have a switch here. So, I am going to move the negative sign into the f, so that this is minus f, correct. And then I am going to have a switch here, which can which can go into can be put to either either A or B, and this basically so now let us say originally the system is in position A. Is there a feedback loop or no? There is no feedback loop. So now let us say I put say cos omega t, cos omega x times t. What is so special about omega x? At this frequency, the loop gain is 1 angle 180. So, AF at this frequency is 1 angle 180. So, what is the signal that comes here? Think carefully, people. Huh? Tatagato Roy. What is the signal I will get there in the time domain? This is a time domain argument. I am putting cos omega x times t, right? I am telling you A times A of j omega x times f is 1 angle 180. What is finally what is the signal at B, man? What will you get? Cos minus cos, I got all possible answers. What is it? You said some f something. So A times f is 1 angle 180, which is minus 1. There is a negative sign. So what do you get here? Cos omega x times t. Is this is this clear to everybody? Okay. All right. So the signal at A and the signal at B are exactly the same. So now suddenly the position of the switch was at A. At some time I suddenly move the switch to position B. What will happen? No change, meaning what? What will be the signal at B? It will remain cos omega x times t, because the signal at A and signal at B were the same anyway. So rather than coming from the generator, you might as well feedback. Take the output at minus f. Correct? So what is this telling you? Now you have a system where you close the loop and the signal here is cos omega x times t. What does this represent? If you take a stable system and you leave it without any input, what will happen to all the signals everywhere? Eventually they will go to 0, right? What is happening here? The signal remains, the same amplitude, does not decay. So this basically means that there are poles on the j omega axis. If there were poles in the right half S plane, what do you think will happen? It will go on increasing exponentially until in practice something saturates and then okay. So this is the meaning of system becomes unstable if the loop gain, angle of the loop gain becomes 1 angle 180 degrees. Okay. All right. So the system definitely becomes unstable with the angle of loop gain being 180 degrees. The angle of the loop gain remaining becoming 180 degrees when the magnitude is 1, right. So in other words, if you want to look at how far is this negative feedback loop from the edge of stability, right, what one can think of is how much phase. So the angle of the loop gain at omega u, So, to prevent all this lag, lead and all that, I'll just take the magnitude of the angle at omega u, right. How much extra phase must I add to the loop gain, right, okay. So, this phi extra phase I am going to call that P sub Pm for good reason, right, which I will explain going forward. So, how much must I add to this, how much phase lag must I add to the loop to make it unstable is a measure of how far I am from stability. So, this is either pi radians or 180 degrees, your favorite, right, okay. So, this phi Pm therefore represents the extra phase lag I must add to the loop to get the system to become unstable, right. So, this so because this is the margin you have before the system becomes unstable, and because it is a phase, this is what is called the phase margin. Does it make sense, right? So, for example, true first order system. What is the phase margin? Phase margin is, well, the lag of the loop gain function is 90 degrees. So, you add extra 90 degrees and therefore, the phase margin is 90 degrees. Now, dominant pole at omega d1, what is the phase margin? Yeah, it is 90 degrees minus 3 tan inverse omega u over omega naught. Remember that this has to be expressed in degrees, right, because we have 90 degrees. Okay, which is basically 3 tan inverse a naught cube f omega d1 over omega naught. Okay, and for omega d2, 90 minus 3 tan inverse a naught cube f omega d2 omega naught, right. So, the moral of the story is that the closer and closer a system is to true first order behavior, the loop gain is the closer the system's loop gain is to true first order behavior, the phase margin will be will be closer to 90 degrees, right. So, in this particular example, phase margin for omega d2 is less than the phase margin for choosing omega d1, right. So, phase margin is smaller, basically means that the margin you have for stability is smaller, which means it is closer to being unstable, right. But what is it that you're gaining when you sacrifice phase margin? What are you gaining? You're gaining back. All right. So, phase margin increases, closed loop bandwidth increases. Phase margin, oh sorry, decreases, thank you. Does it make sense, people? So, to summarize our discussion so far, right? To make a system stable using dominant pole compensation, what do we do? Well, we choose the dominant pole such that the unity gain frequency is much smaller than all the other poles that can occur. In our example, we've used 3 poles at omega naught. It could be 2 poles at omega naught, it could be 4 poles at omega naught, it could be 1 pole at omega naught, doesn't matter, right? And the phase margin is basically the angle, the extra phase you need to add to make the system unstable, and that is that is given by you find the magnitude of the phase lag at the unity gain frequency, and you look at the difference between that and 180 degrees, right? And by adding that extra phase, you make the system unstable. So, that extra phase that you need to add is the phase margin. As the phase margin reduces, your the system is closer to being unstable, right? And what comment can you make with regard to unity gain bandwidth of the closed loop system? It increases, right? So, like everything else, there is a trade off. There's so the so in other words, what this discussion is telling us is that, well, there is nothing holy about making a system behave like a true first order system. Of course, if you do that, you will have a large phase margin, but you will be paying in terms of bandwidth. On the other hand, if you make the phase margin too little, then your system will have a large bandwidth, but is on the verge of being unstable. So, like everything else in life, there is a middle path, right? You don't want to choose a phase margin which is close to 90 degrees, right? Likewise, you do not want to choose a phase margin which is 5 degrees. Okay. So, so somewhere in the middle. So, many people like to use conservative people like to use 30 degrees as the phase margin. People who like to live life on the edge, maybe use 60 degrees of phase margin, right? Yeah, it's the engineer's is the engineer's choice, right?